It's my pleasure to introduce Beatrice Pelloni from the University of Airy in Edinburgh, in Scotland, so also in UK. And so Beatrice is a fellow of the Royal Society of Edinburgh and also a member of the executive committee of the European Mathematical Society, and has research interests in PDEs and boundary variable problems and integrable PDEs, and also some applications to fluid dynamics. So without further ado, it's a great pleasure to hear the talk of Beatrice on the Talbot effect, revivals and special functions. So please, Beatrice.
Thank you, Anna, and thank you, Luke, and the organizers for the invitation. I hope this will be a rather impressionistic talk, and I hope to just give you the flavor of this, which is a sort of side interest. I will say how it's connected to my main research, but it certainly was a sort of occurrence after a talk at a conference that my interest was piqued, as it happens sometimes. I want to also say about the Scotland in here. I just today, because I'm coming to Canada in July, went on to get my visa for the trip, and I had to put in the country field. I looked everywhere: Great Britain, United Kingdom. I couldn't find it. Canada lists Scotland, England, Scotland, Wales, and Northern Ireland separately. It's the first country that I've seen do that. So anyway, Scotland is a country, and that's where I'm working now. And yes, I'm at Heriot-Watt University, but also the Maxwell Institute for Mathematical Sciences, which is really the whole mathematical community here in Edinburgh, including the University of Edinburgh. And it's a very large community and very lively. Why Talbot effect? So this is the guy from which the effect takes the name, and he was a pioneer photographer, also, a sort of polymath, an engineer, but also a pioneer photographer, who in fact, one of the first developed photographic negatives. And in fact, the earliest known we have still in existence is one of his from lattice windows at his house. And that's not quite the earliest known, but it's one of his photographic negatives. And the reason there is this name Talbot effect in my title is that as he was photographing this kind of windows, which are older, large windows with gratings, he noticed a phenomenon that surprised him. And namely that when the light was passing through these gratings on the windows, at a certain distance from the window, say the effect of this grating was reproduced. Not quite at a certain, there were fixed distances at which the grating was reproduced exactly, modulo of course, but sufficiently exactly, but also other distances where it was reproduced in some way. In fact, what he said is that at regular, well, you can read here, he was curious to observe that this grating was out of the focus of the lens, but was perfectly well appearing, perfectly distinctly, and was very well defined. And what this revival of this pattern is what is now known as the Talbot effect, just because he was the first to observe it in linear optics, essentially. The first mathematical studies I know of came a lot later. Okay, so in the 1990s really is are the first articles that I could find about it, and in particular on this phenomenon of reviving of the gratings, which I will from now on probably call without revivals. There were a series of papers by Barry and his collaborators, which model this just by using the linear or free space Schrodinger equation with the initial data just a step function with 1 on the slit and 0 elsewhere. And in fact, once you set it up this way, it's not very difficult to prove that this revival effect should appear. And I will show you how it's really quite not very difficult. But what is more, well, first of all, let me say this has been observed in optics in many other experiments now. and also in quantum, in the revivals of electron wave packets. That's actually where the name revivals was first used. So there are other physical observations, of course, it's wherever is Schrodinger equation or this dispersive linear equation, or a dispersive linear equation of that type that models the phenomenon, you expect to see this. There are, in this case, the parameters are slightly different, but you still see this effect. And there are, if you go if you Google now revivals, you'll find lots of fabulous pictures of this phenomenon now. Okay, so as I said, as far as I know, Barry and his group were the first to investigate this mathematically. It's a linear phenomenon. So free space Schrodinger equation, which is written there, with a step initial condition. Sometimes the linear value, the initial value problem with this type of condition is called the Riemann problem, and periodic boundary conditions. This is, so you're really modeling a periodic grating. And you can prove relatively easily by using Fourier series, the Fourier series representation of the solution, that at times that are rational multiples of the main period, and here I assume that the period is 2 pi, and this will be my period for the whole talk. The solution is actually a finite superposition of translated copies of the initial step condition. So if you have a discontinuity like you do here, if you have a condition that's 0 somewhere and 1 somewhere else, in your solution at these special times, let me call them rational times, they're not rational, but they're rational multiples of the period, the solution will also have discontinuities. Okay, the same type of jump discontinuities as are present in the initial condition. So in a sense, the regularity of the initial condition is preserved at these times. However, at other times, the solution is in fact continuous, though nowhere differentiable. So there is an improvement of regularity, not massive, just one step, but there is a difference in the regularity class of the solution at times that are rational and at times that are irrational. There were, well, I will say, so let me just show you. These are numerical experiments, numerical evidence, or if you want, the numerical representation of this phenomenon. This is the initial condition, this step function. Ignore this vertical line. This is just a numerical artifact. But if you compute the solution at times that are in rational multiples of 2 pi, then you see very clearly that the step function gets reproduced. There is a superposition of step functions that are translated and whose height is changed, but it's just a superposition of step functions, both the real and the imaginary part. There is a real and imaginary part because this is Schrodinger's equation. Whereas if you pick any other time that is not a rational multiple of 2 pi, so a generic time, the solution looks very different. Okay, it's very wiggly. It's nowhere differentiable. This is proven analytically, but it sort of looks like that here. And it doesn't have to be just a step function, just the Riemann problem. If you start with another generic boundary condition, this is a narrow box, and the idea of this is that it approximates a sort of delta function, so to see how this would behave. Again, the same things happen at times that are rational multiples of 2 pi. This narrow box, many copies of narrow box appear both in the real and imaginary part of the solution, whereas at a generic time picked at random. This is not only the case for free space Schrodinger, and this is where I first heard of this phenomenon, Airy equation. So the simplest dispersive third order equation that you can think of, ut is equal uxx. If you start with the same step function, so the Riemann problem for this and periodic boundary condition, and you compute the solution, and this was something that Peter Olver introduced me to in one of his talks. And the reason he was looking at this problem was not because he knew anything about the Talbot effect, but because he was devising exercises for his PDE book. And he thought that this was an easy exercise to ask students to do. So he was computing the solutions of this problem just to make sure that what he was giving as an exercise was doable and reasonable. And just by chance, okay, so if you compute the numbers at the times that you might think are the natural times to compute, you know, various steps of time, 0.1, 0.2, and so on, your solution looks like this, continuous, but not differentiable. But if you suddenly, for any reason, you start computing at times that are multiples of pi, again, this is a different linear dispersive equation, but the same phenomenon appears. These are the original pictures of Peter. And the reason I was interested in this is because the third order problem is very different from the second order one for boundary value problems. So what you give at the boundary really influences how the solution, what the properties are of the solution in a very different way than the second order one. And I immediately thought, is this only true for periodic? Can we change the boundary condition? How do these two things change? So I will speak a little bit about that, but that's why I was drawn to look at this. So as I said, if you stay with this linear problem and look just at the periodic case, it's very easy to see that this phenomenon should appear. And this is because essentially the solution will be periodic, not just in X, but also in T, because of the fact that you can represent it as a Fourier series like this. So there is a periodicity in T that will affect how the solution behaves. And you can write down for this particular initial condition the solution representation in these forms. And this is how Peter computed numerically the picture I just shown by just truncating this series and plotting it. And when you truncate the series and plot it, of course, Gibbs phenomenon comes in all over the place. And it seems to indicate that this may be the origin of all this wiggling once you go to times that are not multiples of T. Because if you look a bit closer, if you look what happens when you just truncate and plot the solution for the truncated Fourier series, there are all these wiggly things that happen at the discontinuities. But these are really a numeric, this is Gibbs phenomenon, and it's an artifact of the fact that I am truncating the Fourier series. For large denominators, you know, if you instead of taking pi over 2, you take pi over 2002 or something, it's very hard to see whether or not this still occurs numerically. It doesn't look very different. This is if it's the same thing zoomed in, and it looks continuous really, and it doesn't look very different from the irrational time solution. But in fact, there is a much more instructive representation that you can explicit analytic representation of the solution of such problems that you can use instead, rather than just taking the Fourier series representation, the first thing that you think of as it is. You can recombine it in a different way and then use essential modularity of the exponent in the exponential, because this is what is at the heart of this, that seemingly looking infinite series really is just a discrete Fourier transform once you couple the terms correctly. And by doing that, and this is something that were first written down by Erdogan and Tzirakis not very long ago, you can write the solution in this form. This is a sort of Gauss type sum, where you can see there are some coefficients. This is a finite sum. First of all, there are some coefficients that are just of a Gauss type sum that you can compute explicitly. It depends on the particular dispersion relation of your linear problem. So here, if you have the free space Schrodinger, this will be just m squared. If you have Airy equation, this will be m cubed, and so on. Then the other term is just it denotes the 2 pi periodic extension, but essentially it's translated copies of the initial condition. So from this expression, you really read what you should expect to be finding. That's only valid at rational multiples of 2 pi. And otherwise, of course, the Fourier series representation is valid at any time. This is only valid at these special times. That's a very nice representation. And in fact, it's also nice to plot. If you plot this, I'll come to that. Actually, you can use their approach, and they proved also to express how these initial discontinuities are propagated in irrational times. It does not say what happens at irrational times, because it's only valid at these rational times, but there is a rather more technical and seriously analytical literature where proofs of the regularity improvement at irrational times are given, and quite exactly, and even the fractal dimension of the shape of the solution at irrational time can be evaluated. Okay, but what I was saying is that if you use this finite sum representation of the solution, suddenly everything is much cleaner. There's no Gibbs phenomenon. There are no vertical lines. You really see this step function revival come through very clearly, both if you have a small denominator or if you have a large one. This is the denominator is 978. This below is what I would get by just truncating the Fourier series. Above is the solution computed by just plugging in this finite sum. And you can see that really is a series of tiny step functions. So this is all very good. And in summary, this was known at this point that at rational time, any initial discontinuity is revived, and at other times there is a regularizing effect on any initial discontinuity, or if you are continuous, you will jump to C1 and so on. There is a one-step regularizing effect. What I wanted to stress is that this irregular oscillatory behavior is not a numerical artifact due to Gibbs phenomenon, or is not even really a limiting effect of that. There is a different mechanism, and there have been works on that as well. So in fact, there has been a lot of work up to 2016, apart from the original observations by Talbot, and then in the 80s of quantum revivals, many mathematical results by Airy and his group, then Peter Olver, when they rediscovered it for the Airy equation, the third order problem. Erdogan and Tzirakis put a whole chapter in their book summarizing all the work that was done. The very first work was done by Oskolkov, but also Rodniansky in the early 90s at irrational times and the regularizing properties. But there's also work since then on understanding exactly in the limit as rationals tend to irrationals, what happens. This is still quite, there is only one paper and is not published on this, but it's well understood by now. What I wanted to know, is this property more general? Is it specific to PDEs with a polynomial dispersion relation, for example? And that's the first, the bit of work we did with Peter and with my colleague Lyonell Boulton at Heriot-Watt. We tried to look at other linear part of well-known integrable wave models, just because it so happens that free space Schrodinger is the linear part of the Schrodinger equation. Airy, the Airy equation is the linear part of KdV. These are all integrable models that very well known in the integrable system and also fluid dynamics community. So it was natural to think of other integrable 1D integrable models that don't have a polynomial dispersion relation and look at their linear part to see whether anything happens. And that's what I will speak about. And it turns out that in that case, there is a revival phenomenon as well. And it's really captured by certain special functions, which was quite nice and unexpected for us to find. I was also interested in studying what happens if the periodic boundary conditions are relaxed, taken more generally, quasi or pseudo periodic conditions, or maybe Robin conditions, and particularly for odd order equations such as the Airy equation. This is quite a non-trivial question. And if I have time, which I don't think I will have because I've already eaten into 20 minutes, I wanted to show you what happens about when you look at the full nonlinear model. Does this survive or not? And there is a lot of evidence and some proofs that indeed this dichotomy between rational and irrational time and this difference in regularizing properties of the equation at these different times survives. And it's not anything to do with integrability, in fact, much to my chagrin, but that's how it is. Okay, so let me talk about the linearized Benjamin-Ono equation, because that's where special functions of a particular type come up, and I hope it makes it, how should I say, appropriate that I'm speaking at this meeting then. So this is the equation we're looking at. The Benjamin-Ono equation would have also plus ux, the nonlinear term, but we look at the linear part of it. It's a non-local equation. Okay, so this nonlinear, this right-hand side is an integral. It's a convolution term, and it's really the periodic Hilbert transform. Okay, so I'm looking at the periodic problem. So it's there is this cotangent term, which you should note. In Fourier space, though, it's a very simple dispersion relation. It's not quite k-square, it's k mod k. Okay, so it's not a polynomial, but is as close to it as you could think of going. It's only one step away. So if you we first of all looked at the Riemann problem. It's not because it's special in any way, but it's because if you look, for example, both for two reasons. One, that you can write the Fourier series representation very easily in this form straight away. And two, if you do numerical experiments, it's easy to check if you get or not this step function behavior in the solution. So first thing you do is you take this Fourier series solution, truncate it just to get an idea of what happens and plot it. So that's what you get when you plot it. This is the solution of this Riemann problem, periodic, at times that are rational multiples of the period 2π. So we started with a step. We don't get a step, but we get something that has a strange and regular appearance at these times. So that I just picked up a few of these times just to give you an idea. There are some places where the discontinuity of the initial condition reappears, but otherwise there are this appear at very regular points. But if you look at generic times, that's not the case. No cusps, it looks continuous, it looks wiggly, very much a different pattern and very much seemingly of the same nature as what happens with the polynomial dispersion ones, Schrodinger and Airy. Okay, so there seemed to be something going on. So we tried to understand what it was going on. And so as we had a finite sum representation that was very descriptive of the phenomenon in the case of the polynomial dispersion relation. So we tried to do the same. We start from the Fourier, for the full Fourier series representation, you try to write it as a finite sum by just putting together things. That's the usual trick. And if you do that in the right way, what you find is that you can write this as a finite sum of special functions that are called trigonometric hypergeometric functions translated at certain points. Okay, so this is what happens when you evaluate this at rational multiples of the period. Okay, so let me just spend a couple of slides on this special function. So these trigonometric hypergeometric functions are just a subclass of what the so-called trigonometric polylogarithms. So I am not really much into special functions myself, but it was quite startling to see something well-known appear here. So that's the definition of this. So what we have is this SJK. In general, they are defined for three parameters, JK and R, and are just the imaginary part of this trigonometric polylogarithm for the case that R is 1. and this is defined for all x's for which this series is convergent, which is all x's except in 0 to pi, except these nodes, which are just rational multiples of 2 pi. It so happens, okay? So we know in the special case of r equal 1, which is the case we have, that's what SJK looks like. I also have the real part of this trigonometric polylogarithms, because it so happens that these functions, the derivatives of this function are arranged in derivatives chains. So because of sine and cosine, of course, they flip from one to the other. And they're obtained by evaluating classical hypergeometric functions on the unit circle. And that's where the trigonometric name comes from. And at the nodes, well, to see what they look like at the nodes, the easiest way is to derive an alternative formula, which involves different named special functions, but I've given it here without a name just to see what it looks like. And so at these particular nodes, both Sj and Cj's, but the Sjk are the ones that appear, have a jump. So the jump comes in the second term, superimposed with a logarithmic cusp that either points up or down, depending on or is absent if at that point the sine or the cosine are 0. Okay, so this is where these cusps come from. We know exactly what these special functions look like, and you can plot them. The cusp is actually infinite cusp. Mathematica cannot render them as infinite. We sort of made them, elongate them manually, but you have to think of this as infinite cusps. And where at the node the sine or cosine are 0, you just have a discontinuity. Otherwise, you have discontinuity and a cusp, and the cusp wins. So this is what they look like. And it certainly starts to make sense of these cusps appearing in the solution that we computed. Okay, everything, if you look now in the digital library of special function, a lot is known about these trigonometric hypergeometric functions. And so we know exactly what the distributional derivatives. I'm giving everything formally, I'm not, so everything can be made rigorous, but let me just give you the flavor of all of this. So distributional derivative of these functions can be computed in this way. And that's interesting. If you remember, in this solution representation of the Riemann problem, so the problem starting from a step function, there were SJKs evaluated, or certain sums of them evaluated at translated points. And the derivative of this have delta functions, which would evaluate anything that you convolve this with, and cotangents, which appear also in the definition of the periodic Hilbert transform. So we are on that looks very interesting. We are on the right track, because what we would like to have is a representation where we can read off explicitly the translation of U0. That's what we had for the other case. We would like to have a representation that tells us that the solution at a rational multiple of pi is given by the sum of U0 translated at different points times some coefficients. We don't have that here, but remember, this is just the solution of one initial value problem. It's the solution when the initial condition is the step function. What we would like is to represent the fundamental solution. So the solution that corresponds to the delta at 0 as an initial condition, because then if we give any other initial condition, the solution corresponding to it is just obtained by convolving the initial condition you have with the fundamental solution. So what we need is to represent the solution starting from a delta function. Okay, this doesn't really make sense as a function. It does make sense as a distribution. So we'll try to formally see what that would look like. Well, we don't start from that, because that's, as I said, it's slightly meaningless, but we start with something that will take us there. So we start with one particular case of our special functions, which is just happens to be the step function, but plus another term, another linear term. And if I start with this, it's easy to compute the solution, and it's given here. But moreover, the derivative of the step function is the delta function, the distributional derivative of it. So if I just, I represent the delta using this particular expression here, so just the initial condition that I have, this special one, plus a constant, I can just formally, by differentiating the representation I have here, get a representation for the fundamental solution. And this is just given by derivative of these special functions translated at these points. Is excellent, because if I will go back to what these derivatives look like, they have delta functions and cotangent functions. And if I have just any generic initial condition, I need to take the convolution with these guys to have a representation of my solution. And when I take a convolution with these guys, this will give me U0 at these points. And this will give me the periodic Hilbert transform of U0 at these points, translated. So if you put all this stuff together, what we get is a result for the revival property for this linearized Benjamin-Ono that just says that at rational time, the solution to this periodic initial value problem, to any periodic initial value problem, is a finite linear combination of translates of the initial condition and of translate of its periodic Hilbert transform. So that's really quite nice, because it's just as simple as could be. It's the best that we could hope. We really didn't have any idea that this would be where we would end up, but that's what it is. So we don't have yet a corresponding theorem, regularizing theorem for generic times, but it's absolutely guaranteed that there will be one. It's just a matter of writing it down. Okay, so let me also go to what happens when you look at other boundary conditions. That was actually the first question I had in my mind when I saw this. And this is not just idle curiosity. So one example, and this was done by Peter with my former PhD student, Dave Smith, in 2019, before I did anything with it, is to look at something that is not periodic condition, but a first approximation of it, which called it pseudo-periodic condition. So they're coupling the solution. This is only for free space linear Schrodinger with different coupling constant, and chosen in such a way that all eigenvalues are real and the problem, so that we can actually compute them. This is relevant for recent results that are motivated by the physics of vortex filaments, and for which they did find this funny fractal plus revival behavior, but had no explanation for. And of course, if these two constants are the same, this is just a quasi-periodic case, which is very important in many other applications. So, and for which actually for Schrodinger, it's easy to solve because you can reduce it to a periodic problem. Okay, but more in general, if the two constants are different, it's not reducible immediately to a periodic problem, though, which, as you will see, it is possible to do that. So there was already this result, which was very technical and involved, very difficult to read why this would be the case from that result, for that first result, but it did tell us that it was reasonable to expect that the revival property would hold also with these pseudo-periodic conditions. But what we set out to do was to reinterpret that result as a sort of, in the spirit of Erdogan and Tzirakis, by deriving a finite sum representation in terms of translation operators and some coefficients that were Gauss type sums. Okay, here actually I've written just the exponential. It's really just the eigenvalues of the particular problems that would be involved here. So we call this particular summa revival operator, and it's just a rewriting of something we already knew. For the periodic problem, for example, it's just writing this Erdogan and Tzirakis sums in operator terms. And so the solution then is just given by the operator of order 2 for free space Schrodinger, the operator of order 3 for Airy, but it's just a nice compact way of writing what we already knew. Nothing new there. But what happens, why does it help when you have more complicated boundary conditions like these pseudo-periodic ones? So if you write it in these terms, you can relatively easily derive that, in fact, the solution is obtained through the solution of 4 periodic problems, which have different initial conditions. So not quite U0, but U0 multiplied by a particular exponential shift and reflected. And so once you have that, if you have 4 periodic problems, you can have revivals for each one of them, and you just add them all up, and writing them in terms of operators rather than sums is slightly neater and easier. But really, it's just, it boils down to breaking up the problem into 4 periodic problems. More elegant and neater, and it allowed us to say a bit more, but this is the first result of, it's not in press anymore, it's in print now, the paper about this. And this would just be a rewriting of a known result if we were at stop there. But we looked also, first of all, of course, there is also smoothing then, because if you can reconduce this to just the periodic problems, all the known results for the periodic problems get through. And so we also know theoretically, rigorously, that at non-rational times, there is regularization of any discontinuity. What we wanted to do is look what happens in the third order case, which is much less obvious. And we didn't do it in full generality. We just looked first at a very specific case of quasi-periodic boundary conditions. So it's not periodic just by multiplication by the same constant for each boundary condition of modulus 1. So a very special case. And we thought quasi-periodic should really be very close to periodic. Revival should hold in this case. We're quite surprised that it doesn't. And it's the first case that in the linear setting, this revival property broke down. And by writing it in this operator form, it's not very difficult to see why this happens. Okay, so we can write the solution of this very special quasi-periodic problem as the solution of a periodic problem with a different initial condition with the third order periodic. So we consider a different initial condition, then we can write the solution of that as the translation of the solution of a periodic problem for linear Schrodinger. So not for Airy, not for the third order problem, for the second order problem, you go down one order, it's a different initial condition, but periodic. And then the solution of your third order problem is obtained by translating the solution of the second order one, but at a different time, at a time that is not rational, because theta is this parameter here, it can be in anything, it's just any real number. So if this theta is irrational, even though you compute this for a rational time, the solution of Schrodinger will be evaluated at an irrational time, and so it will not revive the discontinuities. And in particular, if this theta is not rational, no matter at what time you are evaluating this, the solution does not exhibit revivals. And that's a very marked difference between the third order problem and the second order problem, which is pleasing because the third order problem is different from the second order problem in all sorts of ways when it comes to boundary conditions, to boundary value problems. So that was nice. And of course, you can see that in pictures, they're the same type of pictures. You can see that when theta is rational, you have revival at times that are multiples of 2 pi. But if time is a multiple of 2 pi and theta is not rational, then there is nothing. There is no revival. The solution is regularized, is continuous, and nowhere differentiable. We also looked at n-type boundary conditions. In fact, now we can do any type of boundary condition for linear Schrodinger. This was not done. These are different because they don't couple the two ends of the interval of the 0 to pi. So they're really different from periodic conditions. So we were ready to find that there would not be revival. And we found that the solution was not quite reviving the initial step function. This was just the solution with initial step function at time 0, but there was still something special going on at rational time as opposed to irrational. And indeed, we found that there was a part of the condition that is just obtained as in the revival case by applying these finite Gauss-type sums to the initial condition. So this would just translate the initial discontinuities in a finite number of other places. But there is also another part of the solution, which is actually a convolution, this part here. And so it's a continuous function. So it's a sum of finite discontinuities and plus continuous function. The solution is not simply a superposition of translated copy of the initial condition, but because of this component, it still propagates the initial discontinuities finitely many times. And we call this weak revival. And it turns out, in fact, that this weak revival property is very much more, is common for a large part of, for a large number of types of boundary conditions, and also for, as we will see, for the nonlinear case. So I have maybe 5 minutes left, and I do want to say something about the nonlinear problem, just because that's interesting. Those are the are major PDEs of mathematical physics: Schrodinger equation, KdV equations, Benjamin-Ono equations. Is to be able to say something, and it turns out that for NLS and KdV there is a proof already of the facts, and it's a proof that it was given first by Erdogan and Tzirakis for both equations, that is based on splitting the solution into the part of the solution that corresponds to the linear part of the equation plus the rest, and proving that the rest is continuous. And so it's a sort of situation like this. The solution is one part revival in the, just like for the linear problem, plus something continuous. So it's in fact a sort of weak revivals for the periodic problem for NLS and KdV. What is interesting is that actually numerics seem to imply that this persists. This kind of revival of the discontinuity in the initial condition is a much stronger property than integrability on the nonlinearity. Numerics, of course, show that for NLS and KdV, this weak revival, but also for non-integrable equations that have the same linear parts, such as the quartic KdV. It was difficult to believe these numerics because it's very hard to do nonlinear numerics with discontinuities. The normal scheme, the normal splitting methods and so on, or spectral methods do not behave well when there are non-smooth initial conditions. They break down very quickly. So these were only numerics for very short times. And what happened is there are now very recent numerical schemes that can deal with this. And so one can plot what happens also for the nonlinear problem. And it's very clear that there is a weak revival. In fact, that the revival, this is periodic nonlinear Schrodinger, is very strong. KdV, the same effect. There's something that maybe is Gibbs, or maybe it's just the nonlinear influence of the part of the relation. And this goes on for times that are not just 0, 0, 1. They're quite long. Even for an affine initial condition, we see that revived in some sense, although it's not exactly linear anymore. There is this continuous part that plays a role, but the linear revival property still underlies the shape of the solution. And this is also true for non-integrable. That was a bit, a bit of a disappointment for the integrable people, but if that's how it is, that's how it is. And it seems clear that this is still a weak revival phenomenon still holds. And also for PO, we could use these schemes, which are really very recent. And it's very difficult, let me repeat, to numerically evaluate the solution when there are discontinuities or non-smooth initial conditions. So this was numeric work done very recently by my colleague, ex-colleague, she now moved to Paris, Katerina Schratz, who has this very, very strongly performing numerical schemes that can deal with the non-continuous initial conditions. As you can see, again, also for the full BO Benjamin-Ono equation, the same kind of weak revival pattern, including the Hilbert transform, the periodic Hilbert transform of the initial condition hold. So there is no definition for what this revival phenomenon actually is, but I would say, especially given the evidence that it survives in a weak form for a very large class of boundary conditions and situation, that the most important characteristic, the dichotomy, is really between the level of regularization of the solution that happens at different times. So generically, this dispersive propagation, which all these PDEs share, has a smoothing effect on any initial spatial lack of smoothness, be it a discontinuity or a discontinuity in any derivative. This is at generic times, but at rational time, the initial class of the initial condition will be preserved. So if there are discontinuity in the initial condition at rational time, they will reappear. So there is no smoothing at rational time and smoothing any rational times. So I think this is the dichotomy that really defines what this revival phenomenon is. Kapitansky and Rodniansky, when they wrote one of their first paper in the 90s, titled it, does a periodic particle know the time? Because they were writing about quantum revival. Does a quantum particle knows the time? I think is the title. But we can ask, does a periodic or even quasi-periodic or even non-periodic dispersive wave know the time? That's coded in this smoothing effect. Okay, I will stop here. And there are lots of papers. If anybody, I hope that these slides will be available. I'm happy to make them available to anybody who's interested. So you can look through all the papers that I list that have to do with this phenomenon. But I'll stop here talking now. Thank you.
Thank you, Beatrice, for this very nice talk and lots of revival. So is there any questions or comments or remarks from the audience? Please unmute yourself and ask the question.
One question.
Yeah, so yes, go ahead.
Yeah, it's Julian diffracted, coming from a more photonics and optics background. It looks as though what you've been describing may very well be applicable to mode hopping in lasers, in tunable lasers, where you essentially have bouncing between two mirrors, and you have a dispersive medium in between, and that medium, regenerates light as it's excited. I wonder whether you've had a chance to think about this kind of thing, or whether anybody has done that kind of thing before. So basically, we want to do in the tunable laser is to move the mirror slightly. And you can get a wavelength tuning or frequency tuning, as the case may be. And that's very applicable to optical communications. And that's a situation where it's really important to be able to tune the wavelength so you can, essentially squeeze more data down an optical fiber. So again, the question there is whether that has been considered before.
Well, I don't know this. You're not the first one to bring this up in one form or another, and it's an interesting question that I think absolutely yes. I mean, it should be the analog. This is purely optical light, but I imagine that the laser situation would be very similar, and there should be the possibility of actually tuning precisely using this this way of representing the solution. But I cannot answer for certain if anybody has done it in that particular context. It would seem absolutely suitable to me. It would be interesting.
I think, well, as far as I know, there's been no mathematical solution or modeling of mode hopping issues that happen in optical tunable lasers. And of course, you get it in mazes and so on and so forth, wherever you have two boundaries that are, one moving relative to the other. But it would be a really good idea to perhaps have a look at that.
Maybe
so thanks for that.
Maybe we can communicate on the side or by email.
Yeah, that'll be fine. Thanks. And thanks a lot for your presentation as well. Really well done. Thanks.
Thank you. Are there any questions? Or yes? Yeah, go ahead, Alexei.
Yes. First of all, thank you very much for nice talk. It's very transparent and very clear. And my maybe minor remark is that all this theory of revival can be translated into discrete Schrodinger equation, where instead of continuous line, we have a discrete chain. And in this case, there is nice relation with theory of orthogonal polynomials and with special functions and so on. So there are several works concerning this subject. And what is more important, this also is related with practical perfect state transfer problem in quantum computing. So it's very interesting to relate maybe your continuous model with pure discrete model.
Mm-hmm. Thank you for that.
That's my remark.
Thank you. So is there's still time for questions?
Yeah,
go ahead.
Yeah, actually, it's not a question about this lecture. I don't know if Stefan Kolb is still around or not, but these sort of generalization of Chebyshev polynomials that he mentioned at the end, he raised the issue whether these are classical or not. They are not classical, but they are orthogonal with respect to a absolutely continuous measure, -1/√R2 +1/√R. One can write down the measure, the weight function explicitly if there's interest.
This is with respect to Stefan.
The previous lecture. Sorry, I'm one lecture behind here.
Okay.
Let's